Hi, welcome to the ML project-based course on Explainable AI. In this video, we'll be covering various Explainable AI methods and how we can categorize them. So firstly, there are 4 different ways in which we can categorize the XAI methods. First one is agnosticity. What this means is whether the particular Explainable AI method that we are using, whether that method itself depends on the ML model or not. So whether it depends whether the model is decision tree or neural networks, etc. So that's what agnosticity means. We'll go into the details of this in a moment. Second way in which we can categorize the same methods is using scope. Scope means whether this method applies globally for the entire dataset or locally for a particular instance within the dataset. We'll also see details about what this exactly means. The third way in which you can categorize the same methods is through the data type, whether the method works for image data or text-based data or tabular data, etc. Right? So this is another way you can categorize. And the last way in which you can also think of categorizing the explainable AI methods is the explanation type that this method uses, whether it's visual or whether it is some other way of explaining so that you can interpret the ML model as a human. So that these are the 4 different ways in which you can think of categorizing the explainable AI methods. Now let us look at each of these in a bit more detail. First, let us explore agnosticity. What does this exactly mean? So agnosticity means either the explainable AI method is agnostic to the model, so independent of the model, and there are several techniques: LIME, SHAP, and partial dependence plots. These are some examples. Don't worry at all if you don't know what is LIME and what is SHAP and what are these PDPs. LIME is local interpretable model agnostic explanations. SHAP is Shapley adaptive explanations, and partial dependence plots are also there. These are not the only methods. There are several other model agnostic methods as well, but we'll be focusing only a very few of them in this lecture, the most prominent ones. And we'll be, in future, we'll be having full lectures on some of these prominent methods, but in this lecture itself, we'll touch upon some of these methods in a brief fashion. The other type of explainable AI methods, which are model specific methods. So they will not apply for all models, but they might apply specifically for neural networks or specifically for convolutional neural networks or for decision trees, etc. So there are attention mechanisms which applies only for neural networks. There are tree interpreters which work for decision trees and random forests. CNN visualizer works for convolutional neural networks. So these are model specific explainable AI methods which you cannot use for all models, whereas these models can be used for all types of machine learning models. So hopefully this brings you some clarity about model agnostic versus model specific. Of course, we can. I have written only 3 + 3, 6 different explainable AI methods here. There are several dozens of them. I don't want to write all of them here, but only a few of them to give you an idea. Now let's look at another way in which you can classify, and that is by scope. So scope meaning global explanation versus local explanation. So let us look at each of this, what this exactly means. So global explanation means if there are certain features in the data set that we use for creating, let's say, a classification. If we have a health data set of different patients, and based on this data, based on these different features, we are trying to classify the patient as healthy versus unhealthy. Maybe there is a global correlation for each of these features, which will tell whether in general the patients are healthy or unhealthy. So maybe when we look at the global feature importance, age has very high importance. Maybe age is the number 1 factor which correlates with health. The more old you are, the less healthy you tend to be. And there are several other features also. This is just an example. I'm not even saying this is actually a healthcare related data set, but I'm just giving a way in which you can think about this feature importance. So this is for the global model, meaning this correlation is not for one particular individual. This is the correlation of the model in general for the entire data set. So this is how well age as a feature has importance when it comes to predicting the health condition of an individual. Whereas for local explanation, we are not trying to explain the importance of features throughout the dataset. We are trying to explain for one particular individual what is the contribution of these features. So in this particular case, what is plotted is not a global feature importance, but rather local feature importance for one particular person. So for this person, we can see that glucose has positively correlated with the health outcome. So here red color means high and blue means low, and this is the positive side of the axis and this is the negative side of the axis. Don't worry if you don't know what SHAP value means, you can ignore that for a moment. But basically, if the red color high values are on the positive side of the axis, that means this, and if the blue color values are on the negative side of the axis, that means this variable directly correlates with the final predicted outcome. Whereas if there are some variables where, for example, if you look at this blood pressure, the blue ones, which are low values, are in the positive axis, and red ones, which are high values, high feature values, meaning high blood pressure values, are in the negative axis. What this means is blood pressure for this person inversely correlated with the health outcome in this particular case. So this is the explanation for one particular individual. If you plot the same thing for another particular individual, maybe for that person blood pressure contributed the most. Maybe glucose here will be replaced with blood pressure. So that is the difference between local explanation versus global. Because for global, this is applicable for the entire data set, right? So there are explainable AI techniques which we can classify into these global and local categories. For Lime, SHAP, PDPs, and all these, we can define which of these are global methods and which of these are local methods. We'll come to that. All right. The next classification is based on the data type. So here, the data type we are looking at is text. If we want to classify a sentence as positive or negative, or whether it's a spam or not spam, or whether it is hate speech or not, we will look at the individual words within the sentence, and you can highlight in blue color or red color whether those words positively contributed to the outcome or negatively contributed. So this is how we can explain the decision of an AI model, by looking at the individual data point for text-based data. For image-based data, if we are classifying the images, for example, we can highlight the contribution made by each pixel towards the final prediction. So this is how we will know how much, which part of the image contributed towards the prediction. So if we are trying to classify cats versus dogs, ideally the background of the image in which the cat is sitting, so if the cat is sitting in a park or in the living room, the background should not contribute that much to the prediction. Only the pixels where cat or dog is present should contribute to the prediction, right? And how do we know that in a particular image classification tasks, these are the image pixels that contributed maximum to the prediction? That is using the explainable AI techniques for images. Saliency maps is only one of the methods. There are several methods. We can go through that one by one in this lecture. We can also assign feature importance score for a tabular data set like this. So we can assign positive or negative value. And finally, for graph neural networks, also we can assign importance for nodes and edges. So graph neural network, although we will not be covering in detail in this lecture, I'll give a brief overview what this is. I hope the tabular dataset is straightforward, because the previously shown healthcare dataset was kind of tabular, like glucose, BMI, then blood pressure, etc. So you have bunch of features and you have bunch of values. So it's like a table for every single person. So those data sets are tabular data sets. For graph kind of representation, if you have a e-commerce data set, Amazon for example, if you have data set of users interacting with bunch of items, whether it's adding to cart or purchasing or deleting from the cart, it's an interaction. So you can represent the user item interaction by using these nodes and edges. So nodes are users and items, and edges are the interaction between those users and those items. So in graph neural networks, we can have node highlighting, like a score for every node in the graph, which shows which node contributed maximum towards the prediction. Just understand this qualitatively. Do not worry if you cannot imagine how to implement this, because we will not be covering this detail in this lecture. And same goes for the rest of the text-based, image-based, and tabular datasets also. Don't worry if you cannot imagine how you would be implementing this. That we will come to slowly. But just think about what this data type based classification of explainable AI methods is about. And finally, it's about the explanation type itself. So based on the explanation type, we can classify different explainable AI techniques. So first is visual. So these correlation plots which correlate the variables with each other, it shows the relationship between different variables in a data set. So let me move me up. So here you can see that the wall thickness correlates with wall thickness in a certain way. There is density. So this is a very simple example of a correlation plot. So you have 1, 2, 3, 4, 5, 6, 7, 8 variables here. So here it shows how each of these 8 variables correlate with each other, and you have a correlation coefficient here. So this correlation plot can actually show you how this is a visual way in which you can see how different variables are connected to each other, and also how those variables correlate with the prediction outcome. The second way in which we can show the model interpretability using explainable AI is called feature importance. I know that this graph is it's looking a little bit intimidating, but don't worry about it yet. I will decompose this into individual components. So first look at this yellow line. Ignore everything else, right? So this yellow line shows on an average how does fasting glucose correlate with for this particular data set, whatever is the health outcome. So you can see that high fasting glucose, meaning the positive glucose value above 116, is positively correlated, which is why you have a positive SHAP value. Don't worry if you don't know what is SHAP value. It's not the point of this lecture to explain it in detail, but just understand that a positive SHAP value means there is a positive correlation between fasting glucose and the final prediction outcome, and the prediction outcome could be for this data set about whether the person is healthy or not. So you can think of it that way. It makes sense here, especially. So fasting glucose, if it is greater than 116, there is a positive correlation between fasting glucose and the final outcome. So in general, and you know this, right? If fasting glucose is high, you are generally probably not healthy. And you can see that if fasting glucose is less than 116, there is a negative correlation because the SHAP value is negative. So if negative correlation between the health outcome and the glucose. So the lower the glucose, the better it is, because your health is not, you are not unhealthy if you have a negative fasting glucose, if you have a lesser fasting glucose, because you have a negative SHAP value. So this yellow curve is the average of these blue dots. So these blue dots or cross, these are the actual data points, and you can see its distribution. Yellow is kind of averaging that. This kind of histogram is the distribution of this of the fasting glucose values. So most of the fasting glucose values are around 110 or something like that. That's why you have a peak here. And this histogram on the right is the distribution of the SHAP value. So you can see that it's like a bi model. So there are two peaks, one peak at around 0.1 or something, and another peak at around negative 0.1. So that's how you can read this graph. But what is more important here is to see about the positive correlation and negative correlation. So this is how you know the feature importance, the importance of fasting glucose as a feature. The third one is you can derive model explanations using specific instances from the dataset. And what we are showing here is a classic example of that. So in this example, the task was for the neural network to classify this image as a husky versus wolf. And what was happening was the model was decent. The model was able to classify the image as husky or wolf, but it was making a few mistakes. And that is okay, right? We know that in AI or ML, we won't get 100% accuracy. We will get some, there will be inaccurate results for certain data points. But what was interesting was for this particular data point, the husky was getting classified as wolf. And this is actually a husky, but it was getting classified as wolf. But then when we plot the pixels which contributed to this classification as shown in the bottom image, so the rest of the pixels which are not important have been grayed out, we can see that these pixels, which are actually the pixels that determine whether this is a husky or wolf, is not even considered by the neural network. These pixels of snow is considered by the neural network. So what does that mean? The neural network is actually a good snow detector rather than a good husky or wolf detector. So although the accuracy of this neural network may be very good, it is still not looking at the right pixels. So it's a good insight that we can get from this particular specific data point. So that this is how explanations can be derived from specific data points or specific instances. And the fourth way in which we can classify explainable AI methods is surrogate or simple models. So what this means is, if we have a complex model like neural network or convolutional neural network which explain or which makes a prediction, we could try replacing that complex model with a simpler model with relatively similar prediction accuracy, like a decision tree. So when we replace a neural network with a decision tree, because of the inherent explainable nature of the decision tree, what that means is, we know exactly why a certain prediction was made by a decision tree, because there is a flow, right? It goes from one node, it bifurcates, and then based on the condition, we know which branch to take and then which branch to take. So ultimately we can draw along which branch did the decision making process travel to finally make a prediction or to finally make a decision. So decision trees are highly interpretable in general. So if we replace our global model with a simple or surrogate model like a decision tree, then we can interpret the decisions a bit more easily. So this is another way in which explainable AI can be used for making sense of the predictions made by a complex model. Okay, so now in this lecture, we will be going in details about a few explainable AI techniques. Let me move myself a little bit up. So these 1, 2, 3, 4, 5, 6, 7. These 7 techniques we'll be looking at in some detail, not in extreme detail, but in a qualitative sense. And you can see that the columns here are the 4 different ways in which we can divide explainable AI techniques. So whether it's model agnostic or not. So obviously the value here is yes or no. If it is model agnostic, yes, otherwise no. Data type, text or tabular or image or node or graph neural network, that was also there, but none of these are meant for that. So that's why you don't see that. So there are 3 options here. And global versus local, that also you can see. And then the explanation type, there is visual. Let me go back to the previous slide. There is visual, feature importance, data points, and surrogate / simple models. You can see that here. So you can see that the same technique is model agnostic. It applies for a bunch of data types. It is local. It is also a surrogate model, right? So these 4 ways in which you can classify the explainable AI method applies to all methods basically. So LIME, SHAP, partial dependent plots, tree interpreter, CNN visualizations, permutation, feature importance, and counterfactual explanations. These are the 7 explainable AI techniques that we will be going through in the rest of the lecture. So let's walk you through each of these one by one. First, LIME, local interpretable model agnostic explanations. Each of these words have some meaning. So first, let's start. If we have a data set like this, we have 2 axes. Does not matter what the features are. Maybe x-axis is BMI and y-axis is blood cholesterol. Does not matter. So ignore what are the actual axis values. And these are data points, right? These blue and yellow dots and even the pink dot. These are data points. So what is this? This is the decision boundary of the complex nonlinear model. So all data points above this, this decision boundary belong to diabetic patients, and all these blue dots which belong to below the decision boundary are non-diabetic patients. So basically this complex nonlinear model classifies these points into diabetic patients versus non-diabetic patients. Fine. Now let us look at this pink point in particular. We have a full Lime lecture later, but in this particular slide, we'll be introducing you to Lime. You will not still understand how exactly to implement this in an actual code or for an actual problem, but you will get a basic intuition of how Lime works in Explainable AI. So now, let's say we want to inform this particular patient why he or she was classified as diabetic. Can we say that feature 1 contributed, or x-axis feature contributed more, or y-axis feature contributed more? This is the case of 2 features. What if there are 15 features? Then this will be like a 15 axis, 15 dimensional space, right? So how do we say what features contributed maximum towards this point being classified as diabetic? So what we do in Lime is we zoom in, we look at this feature close up, and what we do is this blue line, what you see here is the complex non-linear model, right? This blue line is this line. We approximate that local blue line using a simple local linear model. That's what we do. So this local linear model in the vicinity of this pink point of interest approximates the global blue model. Of course, this local linear line does not work. So because the line is like this, it does not work for the rest of the model, but it works in the local vicinity of this pink point, right? Then what we do is we generate a bunch of instances around the local point of interest or the instance of interest. So the pink point is the instance of interest. We define a region of interest, and in that region we create these yellow points with black outline and this kind of black/brown point. These are all artificially generated data points, whereas this yellow, this blue, and this pink are the real 3 data points. Rest of the points are artificially generated, perturbed data points. So these perturbed data points are created around the pink point. Now, using this straight line, we can classify these points as whether they are belonging in diabetic category or non-diabetic category, right? And in doing this classification, the points that are far away from the pink point should have less weightage. So this point, these points, etc. are quite far away from the pink point, whereas these points are quite close to the pink point. So the classification of those points should matter the most. And what are we trying to do here? What we are trying to do here is, when the points are if the points are horizontally separated, does that contribute more to the more to a point being classified as diabetic or non-diabetic, or is it more about the vertical? So to give an example, if this point was slightly to the right, then it will be classified as from diabetic, it will go to non-diabetic, right? So it will go from this being yellow to being blue. So don't worry about the color here, because this is just to show the perturbed data points. This is not to show the classification. Don't get confused, because these points are shown in yellow color. So if this point is being classified, what will this be classified as? This will be classified as diabetic. And if we had a point over here, it will be classified as non-diabetic. So for this point, the sensitivity along the x-axis is very high, which means locally, perhaps this feature has very high importance. However, let's say we look at maybe some other point. Let's say we had a point here. I don't have a point here, but let's say we have a point which is somewhere here, or if the line was vertical, imagine that this the dotted straight line was horizontal. Let's say if it is horizontal, then it does not matter whether these yellow points are moving horizontally. Their class is not going to change, but their class will change if they move vertically, which means this feature, the y-axis feature, is what is more important in that case, right? So what this essentially does is this locally interpretable model agnostic explanations. It gives an explanation for which features contributed the most towards making this pink point be classified as diabetic or non-diabetic. Will it apply to other points? Of course not. It won't apply. So the explanation for this local instance will not apply to the rest of the instances or the rest of the data points, but it applies to the local instance. Why? Because we are fitting a linear simple model in the local vicinity of that. So and then ultimately we can create a feature relevance, the relevance of features to that for that particular data set. So if BMI, so here I have written 1, 2, 3, 4, 5 features, whereas here I have only plotted 2 features because there are only 2 axes. But we can't plot 5 axes, right? So but you can imagine that in a 5-dimensional space also we can do the same thing. Then we'll be plotting a linear instead of a line, n-1 dimensional surface, so a linear plane, and then we'll be doing the same thing. And then that's how we know which features or which axis plays a bigger role in classifying the points as diabetic or non-diabetic. So this is how we explain a local instance using LIME method. I am very aware that at this point you may still not be 100% understanding what exactly is LIME and how to implement it in a real problem, but don't worry about that. It's not my intention to teach you that exactly in this lecture, but I just want to give you an overview of these explainable AI methods so that when we go into the details of these individual methods, you're already familiar with it. Now the second method is SHAP, Shapley Additive Explanations. So here what we do is, if we have bunch of features, let's say we have 5 features. So here we had 5 features, 1, 2, 3, 4, 5. We will randomly remove some features and assign random values to that. So to give a specific example, if we have healthcare data set and BMI, body glucose level, cholesterol level, and something else, let's say blood pressure, these are the 4 features that we are looking at. And we have the data of 1,000 patients, and each of these patients have these 4 values, right? And what we can do is we can randomly replace, we take patient 1, and for patient 1 we randomly replace the BMI and blood cholesterol with a random value. Then we randomly replace the other, 2 other parameters, 2 other features with a random value, and we create a bunch of such data points which are not real, only some parts of it are real. So if we are replacing a particular patient's BMI and blood pressure with a random value, with random values, the other 3 features like cholesterol level, and blood pressure, those are actual values, but whichever is replaced is a random value. And this is how we create perturbations. So in LIME we were creating perturbations by changing the feature values. So here in SHAP also we do that, but we only replace some features at each time. And then we send this to the ML model, the complex ML model. And then what we do the same thing in LIME. Don't worry if this axis is bothering you, if you are not understanding. I'll just quickly go through it. So in this particular plot, x1 and x2 are the features, and f of x1 comma x2 is the complex nonlinear model which you see here in this shape, right? So this complex nonlinear model classifies based on features x1 and x2 whether that data point x1 comma x2 belongs to one category or not. And local linear fit means to that particular point of interest, we make perturbations in x1 and x2 or only in x1 to create these points. These red 4 dots you see, those are 1, 2, 3, 4, these features. So in this particular example, you can count that there are 1, 2, 3, 4, 5, 6, 7, 8 features, but on the axis you can see only 2 features. But don't worry about that, it's just a visual representation. So if you have n features, you randomly replace a few features with random values, and then you create a local linear fit, and based on the local linear fit you classify these newly generated points, and based on that we will know which features are contributing more towards the classification, which are the most sensitive features. And why are we doing this random value thing? It's because if we generate good enough number of such points, then the effect of that feature, imagine that we create data points with blood pressure values spanning all ranges. Then what that means is we kind of nullify the effect of blood pressure. We cannot assign 0 value, because if we assign 0, we are assigning an unrealistic value to blood pressure. But if we assign a random value within the realistic range of blood pressure values, then we kind of nullify the effect of blood pressure for that particular data point. I hope at least partially what I'm saying makes sense to you, if not fully, because we are still not going into the mathematical details of SHAP. It's not my intention in this lecture. I'm just repeating this just to make you feel reassured that you are not going into a rabbit hole where you're not understanding something, but just look at it from a distance, and just make sure you are understanding the idea behind this, not like exact implementation. And at the end of it, we will get a feature value versus SHAP value, like the SHAP value versus feature. So this we have already seen in the previous slide. Here for this particular patient, the glucose has a high positive correlation, blood pressure has a mild negative correlation, right? So this is how you read the plot. So the end result of a SHAP explanation for a local instance looks something like this. Right, now let us look at partial dependence plots. Now I hope you are feeling a bit better, because this was already explained in one of the previous slides. If you could not catch that during that time, don't worry. So I'll decompose this partial dependence plot into individual components. First, let us look at this yellow line. Ignore everything else. Yellow line is the average of these blue dots. So we'll come to the blue dots in a bit, but yellow line is the line that we are looking at. X-axis is fasting glucose, Y-axis is SHAP value. Don't worry what exactly SHAP value means. Only understand that a positive SHAP value and a positive, like here, if fasting glucose is greater than 116, the SHAP value is positive. If it is less than 116, SHAP value is negative. What that means is this feature, fasting glucose as a feature, positively correlates with the prediction outcome if it is greater than 116. What is the prediction outcome here? We don't know, because we are just looking at one random plot. Maybe the prediction outcome is the health level. So if fasting, let's say the unhealth level. So if fasting glucose is greater than 116, it positively correlates with poor health outcome or diabetes. If fasting glucose is less than 116, it negatively correlates with diabetes, meaning they are generally healthy. So that's how you have to read the yellow line. These blue points are the actual points, and the yellow line is an average of that. So that's how it is. This histogram, as I mentioned previously, is the distribution of the fasting glucose values in this whole data set. And this histogram, you can see here, is the distribution of the SHAP value. So here you can see the average is somewhere here, it may be 110 milligram per DL, whereas this is like a bi-model. So the SHAP value has kind of, it's mainly focused around plus 0.1 and maybe minus 0.1. So this is how you read the partial dependence plot. So here, by using these plots, you know how glucose as a feature correlates with the final prediction outcome. This is another explainable AI technique. The other technique, which is meant for decision trees or random forest, is tree explainer. So tree explainer, the idea is that generally, if decision tree is simple, it's very easy to interpret decision tree, the decision made by the decision tree, because you look at the node. If the patient, let's say the decision at the node here is whether age is greater than 45 or not. So if age is greater than 45, then you look at the blood pressure. Then if blood pressure is, let's say, greater than 160, then there is a slight risk. Otherwise, there is no risk. I mean, I'm mixing the red and blue color here. Sorry, the green color here. So green is mortality risk, and perhaps red is less mortality risk. But whatever it is, based on the values, so there will be some conditions here: age greater than 45, blood pressure less than 80, or here it could be BMI greater than 25, etc. Now, if we have a patient whose mortality risk is predicted as high by this particular decision tree, it is very easy for us to interpret why that particular prediction was made by the decision tree, because we know exactly the nodes here. But the problem with decision trees is that sometimes it's very difficult if there are a large number of decision trees, or if the number of layers in the decision tree is very large. It's not practical to interpret. So then that's why we have this method called tree explainer. I will not go into details of tree explainer. This was a paper which was published recently, and I'll share the link to the paper in the description of the video. But basically, data using which a tree model makes a prediction, that prediction we can explain. So we can explain which features were relevant, whether age or blood pressure or something else was relevant. And globally also we can make such inferences, and we can also see whether whether features interact with each other. This slide is deliberately made a little bit vague because I don't want to present a ultra complex concept in this video where we are qualitatively going through the explainable AI methods, but just understand that decision trees are normally inherently explainable, but bigger decision trees are difficult to interpret and explain or understand, which is why there is a need for tree explainers. And you must have already guessed, this is a model specific explainable AI technique. This is not model agnostic, whereas these Lime and SHAP methods are model agnostic, right? Okay. Now we have, so this is again showing the tree explainer. So usually a black box model would predict, so with age, BMI, blood pressure and the sex, the model predicts that mortality risk is 4 out of whatever, 10. Whereas tree explainer can give a local explanation. Oh, age contributed 2.5 positively, BMI contributed 0.5 positively, blood pressure contributed 3 positively, and being female is better because it reduced the risk by 2. And this is how the score ultimately came to 2 plus 0.5, which is 3 plus 3, 6 minus 2, 4. So this is a local explanation. So what the tree explainer says is that we can combine local explanation from many samples. By many samples, we mean data like this for many patients to create a model summarization, feature dependence, then explanations, etc. So that is the basic idea, qualitatively the basic idea behind tree explainers. Let's not go into the details of that right now. This is something that I want to spend some time on because this is very interesting, the gradient visualization. For this, I'll be opening a very particular GitHub repository which has
this is the GitHub repo.
I'll be sharing the link in the description. It's a very famous repository. So
here
let me open
there
that
are
and show you. This introduces several CNN visualization techniques. Several of them are based on gradient visualization. So what that means is what is being tried here is to see which pixels contributed maximum towards classifying an image into something. So here Mastiff is predominantly these pixels, right? This is a cat. So ideally the pixels around this should contribute maximum towards the classification. Or if this is a snake, the background pixels should not be relevant because it does not matter what is the background, because for classifying this image as snake, these set of pixels should contribute maximum. So displaying that in a visual fashion, in a fashion that is interpretable for us humans is the idea behind gradient visualizations. And there are many different techniques, but the fundamental principle here is that if you change the value of certain pixels, how much is that going to affect the final outcome? So if you change the value of these pixels, will it change the final outcome that this image is an image of a snake? Probably not, right? Unless you add something very specific here. Unless you add an image of a tortoise here, and if the two classes that you are actually trying to classify are tortoise versus snake, maybe the image might get classified as tortoise. We don't know. But other than that, if we randomly change the value of these pixels, the classification is not going to change. So the basic idea behind these gradient visualization is exactly that. You change the value of pixels, and that is basically a change in input. Input is the image. And see how it affects the output. And output is the classification, the target class, whether the target class being king snake will change to something else, whether target class being mastiff whether it will change to something else, or spider, whether that will change to something else. That's the idea. So this is the original image, and what is shown here is the result from various gradient visualization techniques. So there are so many of them. Before going through that one by one, let me slowly scroll down for you to see how many different techniques are there. There are so many different techniques. You can clearly see here, right? I don't want to go through each and every single one of them, but just for you to get an idea, the plethora of techniques for visualizing various aspects about the gradient. So you can have a look at this score cam. So for mastiff, you can clearly see that the region that is denoted, which are the pixels which contribute maximum towards this being classified as a mastiff, is this. Similarly, for snake, you can see these are the set of pixels, and whereas in score weighted cam, this region here is the set of pixels, and you can see that in almost all the methods. So let us just look at the mastiff for a second and see how much the pixels that are denoted in the gradient visualization is corresponding to the mastiff phase. So here you can see bunch of pixels, but it's also recognizing some pixels over here and here, like these pixels and these pixels being a bit relevant. Here again you can see these pixels and these pixels are the pixels that affect the decision the most, whereas these pixels do not affect the decision in any way. Here again see the pixels which contributed maximum towards the classification. And as you scroll down, you can see various methods shows the same thing in different ways. Some methods are better suited for some kind of data sets. Some methods are less suited for the data sets. And here you can see when that gradient is superimposed or multiplied with the image, the resulting outcome. So here it's very, very clearly visible that these are the pixels that contributed maximum towards the final classification outcome. So this is how we know that the neural network is looking at the actual relevant pixels. If you remember the example which I showed before, the husky versus wolf classification, there the neural network was not looking at the right pixels. It was looking at the snow. Whereas here we can see that the neural network is indeed looking at the right pixels for making the classification. So that's how we know that irrespective of whether the neural network has a very good accuracy or not, the network is trustable. It may have a very high accuracy, but what if these images are being classified as mastiff, but not because the network is looking at these pixels, but rather it's looking at these pixels? It's completely ridiculous, right? Because this is an image of these pixels are like a window, glass window. So ideally, neural network should not be looking at these pixels to make a classification. So this is how exactly we know whether the neural network is looking at the right thing or not. So I highly encourage you to go through this GitHub repository once. It's a beautiful repo. You can even try to fork it and try to run it yourself on some data samples. The other simple yet very effective method is called permutation feature importance. What this means is, if we have 3 data points, sample 1, sample 2, sample 3, and if we have 3 features, feature 1 to 3, and let's say the feature 1 has some values for each of these data points, feature 2 has some values, feature 3 has some values, and for this particular feature sample set, the ML model is making some prediction like this, right? So then what we do is we shuffle the values of a certain feature. So in this case, feature 2 values are shuffled. You can see that 1.1 has moved from middle row to the top one, 2.4 has moved here, and 3.1 has moved from the bottom row to the middle row. So here feature 2 values are not randomly generated, but rather it's shuffled. So that's why we call it as permutation. The feature 1 and feature 3 are intact. And then we again run the same thing with the same ML model, and we see how the prediction changes after shuffling. So this is how we can see how for a particular data set a feature affects the final outcome. So here we'll see that the feature, the changes in these values, we can take a difference from mean, and that's how we can say how important is feature 2 for this data set to make the final prediction, because feature 1 and feature 3 are intact. We can create several permutations of these feature shufflings. We can do the same thing for feature 1 and feature 3, and based on the outcome that is generated, we can get a quantitative estimate of how much feature 1 is important and feature 2 is important and feature 3 is. So this is what is called as permutation feature importance. That's what is written here. It measures the increase in the prediction error after we permute the features values. So the prediction error is basically the value which is predicted after shuffling the features minus the value that is predicted originally without shuffling the features. And another powerful technique is called counterfactual explanations. You might have seen this somewhere. I'll show you. So here also the idea is make small yet measurable changes to the to the data to see what kind of outcomes happen in the final prediction. So to give an example here, the original image, this is that of a tiger. It's predicted as a tiger. Then what we do is we segment the images into 23 different segments here. And then we make changes to some of these segments like as a permutation. So here we were changing randomly the feature, shuffling the features randomly. Here we are not shuffling, rather here we are either graying out or blackening some of these segments. So in the first iteration you will make this segment and this segment black. In another iteration you will make this and this black. And then what we see is what is the minimum change that you have to make to this original image such that the prediction changes from, let's say, tiger to Egyptian cat, right? So that is what is called as counterfactual explanation. So counterfactual meaning what is the minimum amount of change in features that you have to bring such that the final prediction outcome changes, because that's how you know this is the importance of the feature. So now we can see that when we make the values of these pixels black, the prediction outcome changes to Egyptian cat. So what does that mean? What that means is these pixels are extremely important, whereas the other pixels are probably not as important. You can also probably come up with a vice versa argument. Maybe in some cases the pixels that are not black are more important, the other ones are less important. But these are called counterfactual explanations. So in this lecture, I'm just summarizing the models that we looked at in this table summary. You already saw this in one of the previous slides. We looked at Lime SHAP, partial dependence plot, tree interpreter, CNN visualizations, feature permutation, and counterfactual explanations. And each of these explainable AI techniques are either model agnostic or not. They have few different types of data sets on which you can apply that, data types on which you can apply that. Some of them are local, some of them are global, and then some of them are visual, some of them denote the feature importance, some of them look at the individual data point to derive an explanation. So there are various ways in which the explainable AI techniques can be classified. So that was the idea. So through this lecture, I hope you got some idea about different explainable AI techniques, how they are applied for image-based data, tabular data, text-based data, etc. And even though you are still not sure exactly how to implement this in a Python code, at least you got some mental map of, okay, these are the different types of methods out there, and roughly this is how it's being implemented, and roughly these are the ways in which you can classify them. If you understand that much, that is good enough. We'll look at the details of some of these techniques in the future lectures. So these are the references that I used for this lecture. We have a list of papers and some blogs and GitHub repositories. I'll be sharing the link of these references in the description of the video. So thank you so much, and I'll see you in the next lecture.